Hey everyone, this is Dr. Walker. This is video 223. It is called Energy Stored in a Capacitor. So let's look and see how this happens. How does our capacitor store energy? The idea is that it takes work to charge a capacitor. If you think about a capacitor, just your two metal plates here, before they're connected to a battery, then they're not charged. Once you connect them to the battery, so let's put this little battery here with the positive and the minus. Once you connect your plates to the battery, then the negative charges start to flow. So they're going to flow to the right here towards this plate. They're going to accumulate on this plate. And as they do, you can think of them as pushing the negative charges off of the left plates so that you have a net positive charge on the left plate. So the reason that it takes work to charge a capacitor, well, as you keep trying to build up your negative charges here, well, they don't want to go there. They want to be repelled, right? So the battery, there's work being done to push those negative charges towards where they don't want to go. So if you do work on something, you increase its potential energy. This is the energy that is stored in the capacitor. The expression for the energy stored is given in three different ways. And it's easier to look at the first expression, that the energy is equal to 1/2 Q times delta V, where Q is the charge on one of the plates and delta V is the potential difference. This equation should look a little bit familiar because we learned that the change in potential energy of a charge as it went through a potential difference, remember what the expression was? It was the change in potential energy equals Q times delta V. So the reason that there's a factor of 1/2 here is because initially when the charges are being pushed, there's no potential difference across the capacitor. It's only when it's fully charged that the capacitor has the same potential difference as your battery. So you can think of it as the average potential difference is 1/2 delta V, and we get this expression here. The other two expressions come from a manipulation of the equation C equals Q over delta V. For instance, if you solve for Q to get C times delta V, and then you plug that Q into the first expression, then you'll get the second expression, and so on. So which expression to use, since we have three, it just depends on which variables that you know. They both have two variables out of the three variables in the equation, C, Q, and delta V. So whichever two variables you know, that's which equation you're going to use. Let's look at a question. Capacitor 1 has capacitance C1 and voltage V1. Capacitor 2 has twice the capacitance and the same voltage. So how does the energy stored in the second capacitor compare to the energy stored in the first capacitor? Go ahead and see what you can do. The first step would be to figure out which of the three equations you're going to use. So try to figure that out, and let's go ahead and look at it. We're given information about capacitance and voltage. And then, again for capacitor 2, capacitance and voltage. So which equation are we going to use? If we go back to look at the equations, we're going to want to use an equation that has capacitance and voltage. So that's going to be the second one here. The energy equals 1/2 C times delta V squared. So energy equals 1/2 C times delta V squared. With that in mind, capacitor 2 has the same voltage, so we can say, E1, the energy in the first one is C1 and V1 squared, and then the energy in number 2 is 1/2, has twice the capacitance, so 2 times C1, but it has the same voltage, so it has the same delta V1. squared. So you can see the factor of 2 can just come to the front, and you're going to have E2 is equal to 2 times 1/2 C1 delta V1 squared. So the answer is simply that the energy is doubled. It's very important to use the right equation. The reason we could use this equation is because the voltage stayed constant, so we could see exactly how the capacitance affected the energy. If we go back to the equations, there is an equation, the third equation here, that also has capacitance, and if you looked at this one and thought, oh, well, if I double C, then the energy is going to become 1/2, well, that would be incorrect. The reason that you cannot use this equation is because the charge does not stay constant. So if the charge is changing in a way that you don't know how it's changing, you can't use this equation to solve the problem. Hopefully this was helpful, and the fun starts in the next few videos where we finally get to put these capacitors in different combinations and create circuits. I will see you in those videos.